Sorry about the length of that last video. I'll keep this one much shorter. So we talked about the types of light, but now the question is, where does it come from? That's what these diagrams are for. This one here is in no way, shape, or form what an electron actually looks like or its energy levels. This is a diagram used for us to help with the mathematics and understanding. This is the Bohr model of the atom, which is incorrect, but it's a good model to explain what we want to do. So this circle in the middle that's completely filled in, that's the nucleus of the atom. And I see 1, 2, 3 rings outside, and we have electrons filling those different rings. And in chemistry, they'll tell you about how those rings are various energy levels. Perhaps our last one isn't completely filled in. Now, what happens is the electrons are going to naturally want to drop down to lower energy levels. Take something like a light bulb. What we effectively do is we take an electron, excite it through electricity up to a higher level. And then that electron will fall back down. So we used electrical energy to take the electron, raise it to a higher level, and then the electron will naturally want to fall back down into the lower energy state. Lower energy state tends to be more stable. There's more stability there. That's why the electrons move down. Now, in the process, though, we don't get electrical energy as a return. Instead, we get electromagnetic radiation, which comes in the form, if it's a light bulb, as visible light. So this is the wavelength of your outgoing light ray. An example, too, could be exciting elements using radiation from light. So something in like the photoelectric effect could be the light ray comes in, causes this electron to become very excited. The electron leaps up, and it made it to the next energy level, but then it quickly falls back down. It falls back down because there's an open space in the lower energy level, namely the space it just came from. As it falls back down, it re-emits that same radiation in the form of, well, visible light for this example. Okay, now what this diagram shows us is the various energy levels of our atom. Now my atom here, I have ground state, level 2, level 3. My diagram, I put 4 levels. It's really not that big of a deal. The idea is this. Let's say I have an electron here at energy level 3. And I want to free this electron via the photoelectric effect. So an incoming light ray strikes my electron at level 3. What you see here has an energy level of negative 3.2 electron volts. Notice the highest level is called ionization, or N-level infinity, at 0 electron volts. What this means is if I'm at the third level, so at third level, the electron needs 3.2 electron volts to escape. At this point, I could say, all right, well, what's the frequency of light that I need? Now, 3.2 is 4.14 e negative 15 f. Solve for the frequency. And you get 7.73 E14. So any light wave that has this frequency or higher will cause the electron to be ejected. Here's another unique thing about the energy level diagram, though, and this is where your pre-flight tonight on spectroscopy is going to make a little bit more sense of this. Notice that there's no energy level between 8.5 and 13.6. That means an electron can't exist between those two levels. This is part of quantum theory, and that these electrons must exist at specific levels. Level 1, level 2, level 3, level 4. There is no level 1.5. And for the record, too, level 1 is often called ground state. It's the lowest energy state that there is. What this means is I could have an electron on level 4. It could drop down to level 3. That's 2 electron volts. I could run E equals HF, figure out the frequency of that light. I could go from level 4 to level 2. Going from level 4 to level 2, that would be 7.3 electron volts. I could go from level 4 down to level 1. So level 4 down to level 1, that's 12.4 electron volts. I could go from 3 to 2, as well as 3 to 1. And I could finally go from 2 to 1. Notice something here. 1, 2, 3, 4, 5, 6. There are 6 drops possible. That means this particular element would only be capable of emitting 6 unique frequencies of light. Whatever frequency of light, say for example, we got a 7.3, but a 7.0 electron volt wave of light, it would not be possible on here, because between no 2 levels is there exactly 7 electron volts. So it's not possible. This particular element could only emit these 6 frequencies of light. Now, real element is definitely much more complicated than just these handful of energy levels I've displayed here. But I do want to point out that every single element is unique. No 2 elements have the same copy of electron energy levels. And that will become important in spectroscopy. Essentially, though, that's all that we're talking about here. Now, people would ask, all right, coming way back to the very beginning, this purple wave comes in, hits this blue electron, boop, it gets ejected. Could it be possible for an electron to jump from level 1 to level 2? Yeah, absolutely. So the difference between level 1 and level 2, you are looking at 5.1 electron volt difference between here and here. Okay. So if a wave came in with 5.1 electron volts of energy, it would cause the electron to jump from level 1 to level 2. And people often ask, well, what happens next? Usually the electron is just going to drop right back down. Why is it going to drop right back down? Because there's an open spot in a lower energy state. And if it drops to the lower energy state, it becomes more stable. All right, well, that's a wrap.